Good afternoon, everyone. I welcome you to the third problem solving session of NPTEL Combinatorics. So today we'll be discussing the problems from the topics covered in week 3. So the topics that are covered in week 3, the first we have the multinomial first we have a multinomial theorem, which says that number of linear arrangements of n1 objects of type 1, n2 objects of type 2, and so on, nk objects of type k are given by n1 plus till nk factorial, that divided by n1 factorial, n2 factorial, and nk factorial. Second, we discussed weak compositions. So if we like, what is a weak composition? If you want to count weak composition, so basically we are counting number of integer solutions for the following equation: x1 plus x2 till xk equal to n, where xi are non-negative integers. So when we take xi to be non-negative integer, we call it a weak composition, and we can see the number of integer solution for this is n plus k minus 1. Choose k minus 1, which is as follow. So this is basically, so second is saying, so we have to find integer solutions for this equation. So we have n objects, and we want to distribute it among k people, say x1, x2, xk. So what if we want to do that? So what do? We line up all these n objects, and then we start allotting it to x1 till xk. So first, suppose we give two objects to, so we put a line here. So that means two objects go to xk. If we put another line here just after this means that no objects go to x2. So x2 is 0. And so on, we put n. So how many lines we'll have to put? We have to put n minus 1 lines. So there were n, so how many lines? So we have k objects, so we have to put k minus 1 line. So we have n objects and we have to put k minus 1 line. So it is just, so we have n plus k minus 1 positions, and we have to choose the position k minus 1 positions to show where the distribution for a particular person ends. So hence we see that this will be just n plus k minus 1, choose k minus 1. Now third is composition. So for composition also count the number of integer solutions, but we have an additional condition. We have an additional condition that xi should be non-negative. It should be strictly greater than 0. So we can see, if we want to compute these solution, so we have xi is greater than 0. This means xi minus 1 is greater than equal to 0, because if xi minus 1 is greater than equal to 0, so now if we let our yi to be xi minus 1, our above equation changes to y1 till yk is equal to sigma xi minus k, which is n minus k. And here now we have that yi are strictly greater than 0. So finding a solution for x1 plus x2 till xk equal to n, where xi are non-negative, is same as finding solution for this equation y1 plus y2 till yk is equal to n minus k, where yi are greater than equal to 0. And from R2 we know what is the solution for this. So it will be n plus, so since here n is n minus k, so this will be just n minus k. This will be just n minus k plus k minus 1, choose k minus 1. So which will be just n minus 1, choose k minus 1. So we see that this is the composition. So difference between weak composition and composition we have seen. Now fourth thing that we did this week were Stirling numbers. So if we are talking about S and K, it refers, so if you want to count S and K, it refers to number of partition of n element set into k blocks. So this is our S and K. Suppose we want to find S S3 2. So what does we mean? We are talking about a three element set, say A, B, C, and we want to calculate all the we want to calculate number of ways we can divide this set into two blocks. So what are the possibility? A, B, C, B, A, C, and C, A, B. So here we see that S3 2 is 3. So difference between Stirling numbers and compositions are, so when we are talking about compositions, all the numbers that we have, all the objects that we have to distribute are identical. But when we are counting Stirling numbers, these objects are distinct. Therefore, it matters which object we put into which block. And now we have now the fifth topic was partitions. So partition is like weak composition, but we have an extra condition that now we want to get a sequence of number a1 plus a2 till ak is equal to n, with an additional condition that a1 should be greater than equal to a2, it will be greater than equal to ak. So now we see, if we want to, so if we have pk, pnk, and if we have the composition x1 plus x2 plus xk equal to n, how these are different? So if we want to compute a composition, x1, x2, xk can take any values. But if we want to compute partition, we should have a decreasing sequence. That is, x1 should be greater than equal to x2 and xk. So this is how these all composition, Stirling numbers and partitions are distinct. So now we'll solve some problems related to this. Okay. Okay. So our first problem is, we want to find closed form expression for the following expression. So first is summation n over n a b c, and a plus b plus c is equal to n. And we know this term depict basically n a b c is equal to n factorial divided by a factorial, b factorial and c factorial. So we earlier defined that NABC, basically this depicts linear arrangements of n objects, where suppose we have a number of x are a, number of y is b, and number of z is c. So we have seen that by definition NABC refers to linear arrangement of n objects, which is linear arrangement of a x's, b y's and c z's. This is what is NABC. Now we are summing it over all possible possibility. So when we are doing this, what we are basically doing? We are basically, so we have this n positions. We have these n positions, and if we want to find linear arrangements of n objects where we have a x's, b y's and c z's, we are basically choosing, this is equivalent to choosing a positions for x, b positions for y and c positions for z. C positions for z. So yeah, and it is basically equal to n choose a n minus a choose b into n minus a minus b choose c. And this we can, if you open these up, we can see that this will come out to be n choose a, b, c. So now our first problem is we want to find a we want to find a closed form expression for this expression. So here so what is this expression then? So a plus b, a, b, c are varying such that a plus b, c is equal to n. So this expression is kind of computing, this expression is actually computing linear arrangements of n objects. And n objects from the set A, B, C. So we are basically arranging some numbers of A, some numbers of B, and some number of C's, and the total number of A plus total number of B plus total number of C should come out to be total number of X. So if a total number of X, total number of Y, total number of Z should come out to be n. So in a way, for each n position, we have three options, which are basically X, Y, Z. So we see that total arrangements will be, we have n position and three options for each position. So it will be 3 cross 3 cross till 3 n times, which is just 3 raised to the power n. Another way to look at this is, so if we want to compute this expression x plus y plus z raised to the power n. So we know if we want to open this up, any expression here will look like xa, yb, zc, where a plus b plus c is equal to n. But what will be the coefficient? So what will be the coefficient? Coefficient will be exactly n choose a, b, c. This is because when we are opening this, we have this term x plus y plus z happening n times. And now we want to compute the coefficient of x raised to the power a, y raised to the power b, z raised to the power c. So basically, in a way, we are choosing a positions for x, b positions for y, and c positions for z. And this we have already seen. Number of ways to do that is n close n bracket a, b, c. And now the computation that we want to compute is basically when x is equal to y equal to z equal to 1. So we see if we do this in this formula, this will be just 1 plus 1 plus 1 n come out to be sigma a plus b plus c equal to n choosing a, b, c. So this is also, from this method also we are getting it is 3 raised to the power n. So we see the closed form expression for this is 3 raised to the power n. Now our second part is so our second part is we want to find closed form expression for this a plus b plus c is equal to n a multiplied by n a b c. So now we'll use the second method for this. So we have seen that x plus y plus z raised to the power n is just this n a b c, where x has power a, y has power b, and z has power c, and we have a plus b plus c is equal to n. So now we want to compute this expression. So we have a in the multiplication. So if we differentiate with respect to x. The expression that we'll get here will be n x plus y plus z raised to the power n minus 1, and here we'll have sigma a plus b plus c is equal to n a b c, a x a minus 1, y raised to the power b, and z raised to the power c. And as previously, if we put x equal to y equal to z equal to 1, we see LHS becomes n raised to the power 3n minus 1, and RHS is the form that we required. RHS is the form that we required, which is a plus b plus c equal to n, and choose a, b, c and a. So we have found the closed form expression for this also. Now the second question is, we want to find number of surjections. We want to find number of surjections from the set 1, 2, 3, 4, 5, 6 till 1, 2, 3. So what all we need? We need surjection, plus we also need that one should have exactly one pre-image. So how do we solve it? So first we see step 1 is, so since we know first condition is one of the condition is that one should have exactly one pre-image. So first step is choose x belongs to 1 to 6 such that fx equal to 1. So how many ways we can do it? We have 6 options. So we can do it in 6 ways. Now step 2 is, once we have chosen this, second thing is that this function should be surjective. And since x has precisely one image, since one has exactly one pre-image, so step 2 is count number of surjections from 1 till 6 minus the pre-image of 1, which is x, till 2, 3, because none other element can take the value this. So step 1 we can do it in 6 ways. Now we have to find out the number of ways to do step 2, and since these two events are independent, so the answer for 2 is number of ways in step 1 multiplied by number of ways in step 2. So now secondly we have to count the number of surjections. So we can see counting number of surjections, step 2 is equivalent to distribute, I'm saying like without loss of generality, assume x is equal to 6. So step 2 is equivalent to distributing 1 to 5 into two blocks, but here blocks are also distinct, which is 2 and 3. So basically we have to divide this set into two blocks. So we see this is basically Stirling number of second kind for S52, but here since the blocks are also distinct, it matters where the objects are going, either to the box named 2 or 3. We'll have to so we have the Stirling number, plus we'll also have to multiply it by 2 because we can interchange the boxes. So step 2 is this. Now you can calculate what is the Stirling number of second kind. Calculate S52 using your recursion formula. Repeatedly. Using recursion formula. Hello. Hello? Okay. So step 2 is we can calculate. Hello, Anuj, are you there?
Yeah, I can hear you.
Okay. So basically, so this in this question we are calculating surjections from, from 1 to 6, from this uh, elements of set of 6 elements to set of 3 elements, and we also, so we want the function to be surjective, plus we want that one should have exactly one pre-image. So
Okay.
how do we calculate this surjection? So first, since we have that one should have exactly one pre-image, we are fixing the first step is to choose a pre-image of one. So we can, so since we have 6 options, it can be done in 6 ways. Now step 2 is we want a surjection and one has exactly one pre-image. So step 2 is count the number of surjections from 1 to 5, because 1 to 6 minus the x to the 2 3, because none other, because due to this property, none other element can go, any element except x cannot go to 1. So now we are so our problem reduced, so our now problem reduced to counting step 2. Now, if we want to calculate step 2, it is equivalent to distribute these element 1 to 5 into 2 blocks. But here also our 2 blocks are not identical, they are numbered. So it matters where we put our numbers into. So we have 2 blocks, 2, 3. So if we had to distribute these objects into 2 blocks, it would be just the Stirling number of second kind, which is we have S52. But now here boxes are also distinct, so we can interchange the boxes, hence we are also multiplying by 2. Is that clear?
Yeah, I need to. I'll check it later. I
Okay.
joined very late.
Yeah, sure. So now this is, so now you can calculate this S52 using your recursion formula repeatedly. So okay, now this was one way. Another method for step 2 is step 2. So you want to count surjections from this 1 to 5 till 2 3. So first of all, what are the total number of functions? Can you tell? Like if you want to calculate the total number of functions from this 1 to 5 to 2 3, what are the total number of functions?
Total number of function for one, we can have two choices. For
Yes,
each of the element, we can have two choices.
yes, yes.
2
So
raised to the power
2
5.
raised to the power 5. But we have to calculate the surjective functions. So we use the principle of subtraction. So for we can see here it is easy to count non-surjective functions. So since here in the codomain we have two objects, any non-surjective function is a constant function.
Yeah,
And how many constant functions do we have?
2.
We have exact 2, because either everything goes to 2 or this. So we have 2 constant functions. So how many, so number of surjective functions become 2 raised to the power 5 minus 2.
2.
So and the final answer becomes, so there were 6 ways to do step 1, 2 raised to the power 5 minus 2 to step 2. So our total answer becomes this. Okay. So now our next question.
Can we discuss the assignment problems?
Yes, we can discuss, like we'll discuss it in, like I have like after these problems we can discuss
Okay.
it.
Yeah.
Yeah. Okay. So how many, next problem is that we have to find how many 3 element subset does this have. So so we have 3 A's, 3 B's and 1 2 3 4. So how many 3 element subset does this have? Suppose we denote xi by number of I in set. So finding 3-element subset, our problem is equivalent to finding the solution for this equation, that is xa plus xb plus x1 plus x2 plus x3 plus x4 equal to 3. So but we also have some restrictions. We have that xa should be less than equal to 3, xb should be less than equal to, xb should also be less than equal to 3, and x1, x2, x3, x4 should be less than equal to 1. So can we say that it is equal, so this problem is equal to calculate the compositions?
But
No,
here, when we select the
hmm,
means A's we are selecting, the number
hmm,
of ways is always going to be 1, whether I select 1, 2, or 3.
hmm, yeah, yeah,
So
yeah,
it's better to approach, I think, the coefficient of x raised to the power 3 in the expansion of,
hmm,
if for A's we can write 1 plus x plus x square,
hmm,
next cube. And
yeah,
similarly for the 3 B's. So 1
hmm,
plus x square plus x cube raised to the power 2.
hmm,
And in the next bracket, 4 brackets of 1 plus x.
yeah,
So that is 1 plus x raised to the power 4.
yeah, yeah, yes, we can do it like that. Yeah, okay. Also, alternatively, we can also do this, like this is like if we want to use the composition method. So see, since here, if we want to look at like the composition, so since the n here is 3, so it would have been a composite, it would have been a composition if we don't have any, if we have we have that xi, it should have been a weak composition if it would have been that each xi should be greater than equal to 0 and we don't have these additional conditions.
Hmm.
But here in this case, we can see that this condition and this condition is kind of redundant, because xa, like xa and xb can in this solution can never be greater than equal to 3. So when we are talking about a and b, it is still a weak, it can be treated still as a weak composition, but we need to worry about these integers 1 2 3 4. So if we want to find 3-element subset, our first step can be, first we choose our integers, choose our first we choose our k integers, and second is, step 2 is, then we choose an n minus, so since we have find 3 element subset, we choose a 3 minus k element subset, 3 minus k elements subset of 3a 3b, right? Is this fine? Like, why we can do this?
Yeah.
So now for step 1, we know if we have to choose k integers, so we have 4 integers, so step 1 can be done in 4 choose k ways. And for remaining, for the step 2, we have we have to solve this composition, because we have to choose 3 minus k letters, 3 minus k objects. xa plus xb should be 3 minus k, and our condition that xa should be less than equal to 3, xb should be less than equal to 3 is kind of redundant. So this is basically a question of calculating weak compositions, and we know number of weak composition, we know what are the number of weak compositions for this. It is basically 3 minus k plus 1 choose 1, which is 4 minus k choose 1. So, so, so our answer here becomes, we are summing over k going from 0 to 4, 4 choose k into 4 minus k choose 1, which is just 4 minus, k. And this is also, and this we can further write it as k equal to k going from 4, 4 choose 4 minus k, 4 minus k. And this expression we already know, we can find a closed form expression for this. So basically we are, this problem is equivalent to choosing a subset of 4 elements choosing a subset of 4 element set with a distinguished element. So this will be just, first we choose the distinguished element, which is 4, and then we choose a subset which is 2 raised to a power 3. So we see this is our, this is one of the ways to do this. Is this fine?
Yeah.
Okay. Okay, so our next problem is this. We want to count the number of partitions of 11 in which difference of first two parts is at least 3. Any idea of how we can do it?
No,
Okay, yeah.
I have
So,
not tried yet.
okay. Yeah, so like we'll so when we have to count partitions, we'll try to simplify it. So we'll see, so the set that we want to calculate, that is partitions of 11 in which difference of first two part is this, we call it A, and our claim is that this A is in bijection with set of partitions of 8 with at least two parts. Okay, so if I'm saying this claim, can you think like how can we construct a function? So here we have a partition. So here we have a partition x1 plus x2 plus xk equal to 11. And since it is a partition, we know that x1 is greater than equal to x2 is greater than equal to xk. And we have also another condition that x1 minus x2 is greater than equal to 3. So can you, using this partition, can you give a partition of 8? So because we have x1 minus x2 is greater than equal to 3, we can see that x1 minus x3 is greater than equal to x2. So if you have to give me a partition of 8, you have to basically give a sequence of integers of a decreasing sequence such that the sum come out to be 8.
This set of partition of 8 with at least two parts.
Yes.
This I didn't get. How is it possible?
Yes, this is what I'm proving. So if we are showing that the set that we want to calculate is in bijection with this set.
Nay, how specifically we are thinking about this part only? Why don't we have another thing?
Yeah.
A set of partition of 8 only with at least two parts.
Yes. So see why specifically we are thinking this. So so we can backtrack a little. So suppose we have a, so we want to basically simplify this problem into a simple problem. So our conditions is that we are given a partition which is x1 plus x2 till xk, whose sum is 11, and we have additional condition that x1 minus x2 is greater than equal to 3. So if you want to act, so if we want to count these directly, it might be a problem. But now since we have this condition x1 minus x2 is greater than equal to x3, we see that this condition is equivalent to saying that x1 minus 3 is greater than equal to x2. So we can so if we use this, we can see that this will give, so if we subtract from 3 from both sides, it remains to be a partition.
Okay.
It remains to be a partition because x1 minus 3 is greater than, and since 11 minus 3 is equal to 8, it becomes a partition of 8. So when we write it down, we see that we are getting a partition of 8. So now our guess is, so this was our intuition. So from this we are getting a partition of 8. Now our guess is if we can see that this function is injective and bijective, then calculating partition of 8 is simpler than calculating partition of 11. So we have simplified our problem. So now we want to see that this association do give us a bijective function. So if we want to see that, so it is sufficient to construct an inverse. An inverse can, so if we want inverse of a function, so suppose, so we have a partition of 8, y1 plus yk equal to 8, y1 is greater than equal to y. So if we want to construct an inverse of this function, so we have to send it to the partition of 11. So we do the inverse operation. We basically consider this partition, y1 plus 3 plus y2 plus yk equal to 11. So we saw set of partition of 8s we were getting from this. But why do we need at least two parts? Because we need this condition to be true, that the second because in the partition of 11 we need at least two parts. So in the partition of 8 we also need two parts. So we see that these two sets are in bijection.
Okay.
And now, so now you just have to calculate set of partitions of 8 with at least two parts. So we have, it is basically, the answer is P8. And what partition you have to subtract? Partition with one part, which is exact, we have just one partition. So the answer will be P8 minus 1. Okay.
Okay.
Yeah. So next question is from your class. So if you did you try attempting this? So it was during, like, one of the problems left in class. So it is that 20 people entered in a queue to buy latest Harry Potter book, which cost 100 rupees each. Sale counter has no cash. If exactly 10 people have rupees 100 notes and rest of the people at 200 rupees note, what is the probability that no one has to wait for change? So 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 what we have to do? So we have to basically arrange 20 people in such a manner,
No.
arrange 20 people in such a manner that counter sale counter does not require change. So how can we do that? So we see, if at the first position, person with 100 rupee, so I am calling person with 100 rupee note as P1, person with 100 rupee note, and P2, person with 200 rupees note. 200 rupees. So if we want to arrange 20 people in such a manner such that sale counter does not require change, so person with 200 rupees note can't approach first. So first position
Yeah.
should be occupied by P1. And
You can 200 and 100, they can interchange themselves
yeah,
because 200 should come after the 100.
yes,
Each of the 200 then can be done.
yes. So basically what you are saying, that at each position, like at each kth position, number of people with 100 rupees note should be more than number of people with 200 rupees note, right?
Hmm. Hmm.
So can you think, like, from previous lecture, if we have some similar kind of situation, like we wanted that some things, number of people with 100 rupees note should be always greater than number of people with 200 rupees note. So what we are doing first, our first step is we are calculating number of ways, in which we can fix positions for people of type 1 and people of type 2. And what is our condition? That at each kth step, like if we are first kth step, at each kth step, number of P1 should be more than number of P2. So any guesses how can we solve this problem?
Just a second.
Yeah. we like we have some like matrix problem also. When we were asked to put the brackets, we had two types of brackets and we wanted that all the left brackets should come.
Yeah, yeah, I remember
Okay.
something like that. But
Yes. So yeah, so like, so this is basically, so let's say it is related to lattice paths, counting
hmm.
counting
Just
le-
draw the diagonal over there
yeah,
and just try to keep always above the diagonal
below the
or below the
below
diagonal.
the diagonal.
Yeah, we can define whichever way is the
Yeah,
100 or
which
200
are the,
comes.
so yeah, so if we are taking right step, if right step corresponds to that people with 100 rupee note, the note, and upward step corresponds to people with 200 rupee note, 200 rupee note. Okay, we want to calculate north east paths on 10 cross 10 block, because we have 10 people with 100 rupees note and 10 people with 200 rupees note that lie below the diagonal. Is that fine?
Hmm.
And this you have already calculated in class. This was coming out to be, here n is equal to 10. This was coming out to be 2n, which is 20. Choose n minus 20, choose n minus 1.
Yeah.
So this is the ways to, so now we have basically get the positions where, so number of paths, number of positions, these are the number of positions. But are we done? We have to but we have to find the linear arrangements, right? Right now what we have got, we have got an arrangement of 20 people where we know, so we, these are the number of arrangements of 20 people where number of people of type 1 will always be greater than people of type 2 at each kth stage. But these type 1 people can also shuffle, right?
Yeah, they can
Yes.
interchange
Yeah.
themselves
So in how many ways? 10 factorial. So
into 10 factorial into 10 factorial.
yeah, 10 factorial into 10 factorial and into this number of paths. So if I call this quantity A, so A.
Hmm.
But we have to calculate the probability. So and total. So this is the favorable outcomes, number of favorable outcomes. So what are the total outcomes? Total outcome are the total arrangements. And what are the total arrangements of 20
20
people?
factorial.
20 factorial. So is this problem fine?
Yeah, I understood.
Yeah.
A very good application of lattice points.
Yes. Yeah. We are basically using two things here. We are also arranging them and we are also using the lattice.
Because
Uh,
linearly, if you think the arrangement, then it will become very difficult.
yes, because like at
For every situation, there will be a different kind of cases will arise.
yes, yes. In that way only you can see that we are thinking of computing linear path, because in linear paths, like why this problem corresponds to linear path. So in
Hmm.
linear paths also, when basically at each position, like the next position depends on the previous position, and
Exactly.
there are many ways to calculate previous position, hence we
Right.
calculate the possible lateral path. So it was basically a similar problem. Okay, so now we can discuss the assignment one that you were some.
Yeah.
Yeah. So do you want to discuss the first problem first or second
Yeah,
problem?
please. Please. Second, I got it, and actually,
Second
the
one, yeah.
second letter I realized. Actually, what I
Hmm.
was thinking
Hmm.
when we have pigeonholes, we have considering the prime powers of exactly one, means 3 raised to the power 1, 5 raised to the power 1,
Hmm.
11 raised to the power 1.
Hmm.
And from there, when we pick any two elements and multiply,
Hmm.
then the x1 into y1's square root will not going to be the square.
Hmm. Yes.
But other than one power, if I have like 3, 5, 7, 9, even if we multiply with a one power, we can get the square root as a square itself of x1, y1.
Okay. So you are saying So I didn't understand. Like, so you have like, so the possible were 2, 3, 5,
Mm.
7, 11, 9. Oh, sorry, two, not 9, 11,
30,
13, 70. There were 8,
nine-
3, 4,
19.
5, 19 also. Yeah. So what you are saying, your if x1 is this, yeah, some power.
Ah.
Hmm.
Even power, any other power, let's say we decide that 11 and 13, because all the possibilities we have to count.
Yes.
And that possibility, see, if anywhere we are keeping the power 1,
Hmm.
exactly 1.
Okay.
So we can have the 8C1 possibilities.
If AI is equal to 1, yeah.
And we are keeping at two prime numbers, we are keeping the power exactly 1. Then 8C2 possibilities I can have.
Hmm.
The
Okay.
8C1 plus 8C2 plus 8C3 up to 8C8, that is 2 raised to the power 8 minus 1.
Wait, okay. So you are
So that part we have omitted, where we are getting the single odd power, the one odd power.
okay.
And other than this, if we get, then we will multiply, then automatically we'll have a number whose square means x1 y1's square root will become a square.
So you're
Because we have sufficient number of pigeon holes are given, that is 769 were given, which can be
yes,
written as
yes.
a,
Yeah.
because
So
because in this if any two
so
numbers we choose,
okay. So basically, what you are doing is you are removing all those holes which have exactly one power. Are you
yeah,
doing?
one power,
So so if and number of such holes are basically
2 raised to the power 8 minus 1.
2 raised to the power 8 2 raised to the power 8 minus 1. Why is that? Because
Because anywhere, any of the 2 up to 19, any of the prime, I can put the power 1,
hmm,
8C1 ways.
yeah,
Any two places, and rest of the places can have the even powers.
hmm.
Because that way we have decided the pigeonholes. No?
Okay, what were your pigeon holes? Yeah, pigeon
Even and odd powers
even
means
and
odd.
odd powers. Yeah,
Yeah.
okay.
So this we need to remove there. Because from this, if anywhere you, let's say 7 raised to the power 1 is there,
Hmm,
and 17 raised to the power 1 is there,
hmm,
and rest all are the even powers are there.
hmm,
And again, we change somewhere the even power. 17, I change the even power, and 7, I keep the power 1. So that
hmm,
will belong to the same,
hmm.
that it's a
But
different.
but see, like the like I don't like. So see, if you have an even power also here, like suppose 5 has a power even 2, and another number has power say 4. So when you are multiplying it, you are getting a even power, but you are not
Yeah,
getting a number like you are not getting a you
uh,
are you are not getting a
there we will get.
hmm.
There we will get. Let's say 5 raised to the power 1 is there,
Yeah, 5
and
is
then
the
the
power.
same 5 raised to the power 1 is there.
Okay.
Because it's only about even and odd is there. Huh?
Yeah, yeah.
So now if I multiply 5 raised to the power 2 will get.
Yeah, like see if
And
yeah.
then the
Hmm.
square root of this will not become a square.
Yes, yes.
So
Square.
that's why we need to remove those numbers, I think. I may be wrong somewhere.
Okay. So I'm like okay.
I
Yeah.
hope you're getting my point. That's why I
Hmm.
was thinking for
Hmm.
remainder with having 0, 1, 2, 3, 4.
Yeah. So I have a should I have a different approach. Should I tell that?
Yeah, please tell.
Okay, so basically, yeah. So as you said, we have like 256 holes.
Mhm.
Because 256 holes, basically, we have for this corresponds to parities of each of the power, like whether it
Correct.
is odd or even.
Correct.
Now
Yeah.
we have 769 integers.
Mhm.
Okay, so whenever your n is strictly greater than 256, you can
Mhm.
always guarantee by pigeonhole can guarantee a pair x1 x2 whose product is even,
Yeah,
whose
that's
product
correct.
is square. Yeah.
Yeah, that will be
Huh.
correct in all the possibilities.
Yeah. So yeah. So now like see. Suppose we have 769 integer. So since it is greater than 256, we choose two integers. We can always find two integers which are going to the same hole. So x1 x2 will be a square. Fine.
Mhm.
So we take this pair. Now we are left with 767 integers. Again, 767 is greater than 256. So we can get another pair, say x3, x4. So if we keep on doing this for n equal to 256, for k equal to 256, that is if we do it 256 times, we find, so 769 minus, so if we are doing it 256 times, basically we have 256 pairs which has with, so we have 256 pairs whose product is even. So this is 769 minus 256 is 257. So we can, since 257 is also greater than 256, so we can find 257 pairs. Are you getting? So from 769 integers, from 769 integers, we can find two seven two two 257 pairs of integers. So we have P1 till P250, 257, and in each P1 has x1, say x1, y1, and so now all these pairs, so these are non-repeating. Basically, if we have taken two integers, the next two integers are different from these because we are removing all the previous pair. So did you understand? Like, so we can get
I
250.
need to take some time to think it. Means,
Yeah, yeah.
yeah, I'll think it over. But what I said, I hope you understood my
Yeah, yeah,
point too.
yeah, yeah.
We have taken out those where we cannot get the product of two numbers square root as a square.
Hmm.
Because if I
But
keep the exactly
like,
power
yeah,
one, yeah,
yeah. But like, if I don't understand what do you mean by taking out, but it can happen, right? That all, you can't take these
if
out.
I keeping
All those,
odd powers exactly one.
huh? Like it, like odd power. So basically, you are removing a parity of this type, right? 2 raised
Yes,
to the
yes, yes.
power 1.
Moment we remove and when we take the two numbers, then their product will automatically become the
Huh.
square root.
But you can't, like, we can't remove this, no? Like, because like it, like if you have these 769 integers, there can be a possibility that all 769 integers are following in this.
How it is possible? If I'm exactly power one, I'm giving exactly one. I'm not talking about three.
Yeah.
One, if one and three are multiplied, then automatically the summation will become four.
Hmm.
And the square root, if I take, it will remain a square.
Hmm.
So actually, those we have removed by 8C1, 8C2, 8C3, and they're adding, we have removed that number. Is
Okay.
it correct?
I am sorry, like, so you are removing the, so first of all, okay, we are doing pigeon, we are using pigeon. What are your what are your holes? It's fine. Like in the, what are your blocks? Hello.
Yeah, I
Huh.
can.
So
Blocks are the even and odd parity
even an
only,
odd
nothing.
parity. So we have
Yeah.
basically 2 8 raised to power 8, 256 blocks.
Hmm.
So now you are saying you are, so you are removing the blocks, removing those.
No, we are removing those pigeons which can create the problem for us.
Okay, but like, but how do you guarantee that you, like after removing those pigeons, you left with some more you left with some pigeons? It can be a possibility, right, that all your pigeons are creating that same problem.
Means we can have the even powers up to infinity that way.
Even powers up to infinity, as in?
No, I'm thinking my means 2 raised to the power. Let's say one other I take 2 raised to the power 2, 3 raised to the power, and
No, you,
just give. I'll discuss in the next class. Will I need to sit and think about it.
okay, fine. Yeah, yes, we can discuss.
First one, can you tell me how to go ahead?
Yeah, yeah.
First.
Okay, wait. So first one was, okay. Mm, yeah. So first one, you have 10 teams. So we were this as 10 teams. First you had 10 teams. So you have total matches were 45, right?
Correct.
Total matches were 45. Winning
Hmm.
had +1, losing has -1 score, and draw has 0.
Hmm.
And you had that 70% were drawn.
Hmm.
So deciding games were less than 13, I guess, like when you say less than equal to 13, right? Deciding games were less than equal to 13. Now deciding games were less than equal to 13. Since we have 10 teams, so we are creating our blocks as teams with non-negative score and teams with negative score. So we have these two blocks, suppose. Fine. And we have 10 teams. So we can guarantee that at least 6 teams will be in one of these blocks. Right? That is at least 6 teams. So we can say at least 6 teams will either have all negative scores or all non-negative scores. Fine. So now case 1, suppose they fall into the box 1. They are in box 1, that is all teams have non-negative score. So we have 6 teams with non-negative score, and suppose none of them have same score. So what are the possibility? It can be 0, +1, +2, +3, +4, +5. Okay. So if all the scores are distinct, this can be the least possibility. So we see that this sum out to be 15. But the deciding games were 13. So so if all the teams, so we know at least, so by case 1 we know that at least 6 teams have non-negative score, and further if we assume that all have distinct score, so if all have distinct score, if we take the minimum possible scores of all the teams, it is 0, 1, 2, 3, 4, 5, and it is adding up to 15. So that means at least 15 matches were played in which 15 matches were played where the score was decided. But we have that the score was decided for less than 13 teams. So this is not possible. So if they are in box 1, at least 2 of them have to have same score. Is this fine?
Yeah, I'm trying to understand.
Yes. So see, so pigeonhole principle, we used it for this thing. So we have 10 teams. So suppose, and we are listing out its score. So we want to show that at least 2 teams have same score. So first, our first box is that teams with non-negative scores, and second box is team with negative scores. Now if these are the 2 boxes, by pigeonhole principle, at least 6 teams will go in one of these boxes.
Why we are keeping these 2 boxes only? Because the possibilities may be others also. No?
But these are the exhaustive options, right?
Okay. Negative and non-negative.
Negative and non-negative, these are the exhaustive options. Sorry, hello.
No, doesn't.
Did you understand? Hello. So these 2 are exhaustive possibility, that either a team will have a non-negative score or it will have a negative score. Hello. Yes.
Yeah, I can hear. Hear.
So it will have either a non-negative score or a negative score.
Okay.
Now, so suppose they have negative score, suppose they have non-negative score, and all are distinct. So the minimum possible addition of these scores is 15. But we know that at most 13 matches were played which had a deciding score. So this cannot happen. Right?
Hello. Yeah, I can hear.
Yeah. So
I'll think it then this ground again.
Yeah. And And similarly, you'll see if they are if the second box is with all negative score, the minimum possible scores is -3,
Minus 6. Minus
minus
6.
5, -6, which will come out to be -21. So this means that at least 21 deciding matches were played. So this can also not happen. So you see, you get a contradiction.
But the
So
simultaneously will all this situation will be occurring.
no, no, simultaneously
So
all.
in totality, you have denied the statement. Okay,
Yes,
okay,
yes,
okay.
yes.
Yeah.
Be-
Correct. Very good. Yeah. Good one.
yeah,
Yeah. Now it's clear.
yeah. So you can think about both these problems. Like if there's a, you can think about both these problems.
Yeah.
Yeah. So do you have any other doubts?
The assignment two or the
Okay, so
last two doubts were.
okay, so yeah, so today I think assignment 2 we can discuss next time. Do you have any doubt from
Okay.
assignment 1?
No, 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 no. Assignment is clear.
Yes. And today's problem, find week 3 problems.
Yeah, it's good. It's actually I joined little late, so
Huh. Yeah, yeah, I'll upload the video and
I'll
the
see
notes
it.
also. Yeah. Okay. Okay then, like if you have no
Yeah,
problem. Okay.
yeah. Thank you so much.
Yeah, yeah, no problem. Okay. See you next time.